I too will do my best to get us to an early lunch. But we'll see how that goes. Over here on the side, I want to put some hypotheses. I'll never remember to keep saying them. So our X Pn is a smooth, non-degenerate variety. What do I want? H I X O X K is 0, I K greater than or equal to 1. I want a 3 very ample embedding. And I want it to satisfy N2. So 3 very ample again means 4 points span of P3. I'll add one in a little bit, but I want to explain it.
Or N2 or ND?
And 3 very ample and satisfies N2. So for curves, N2 will imply 3 very ample by the general. Okay, so what do we know? Remember this from last time, which I guess yesterday. We know his first secant variety is normal. We know it's smooth away from the variety. We know that if we blow up along X, we get a P1 bundle. Over the Hilbert scheme. We know the intersect of the exceptional divisor is precisely the universal divisor. The Hilbert scheme is supposed to be a delta. And notice that because Hilb2 is smooth, problem transfer the secant variety is smooth, or the blow up the secant variety is smooth. Same thing. Okay. So the first result, which I had intended to get in at the end yesterday, but ran out of time. In the case of curves, with curves degree 2G plus 3, 2G plus 3 is precisely what's needed for the very ampleness at N2. You think about what we should want to happen. If you remember our picture yesterday, properties of the secant variety at 2G plus 3 should be related to properties of the curve itself at 2G plus 1. So, we know about curves embedding degree 2G plus 1. We know at least 2 things. We know that these curves are 3 regular, and we know that they're arithmetically Cohen-Macaulay. So we should look for related properties up here of the secant variety at 2G plus 3. As luck would have it, this works out perfectly. So first, the ideal secant variety is 5 regular. and that's sharp. And second, secant variety is arithmetically called Macaulay. And this was joint work of myself and Jessica Sidman. This will appear at some point in the future. I don't know. Sometimes it takes a while. There's no way it'll get out this year. There's no way it'll appear this year. So this, and I'll talk more about especially this first one in higher dimensions. This fits exactly what we hoped would happen. Before we get overconfident, though, not everything works so nicely, and this at least keeps things interesting. Now that this works at 2g plus 3, the next thing you should think about is, what about canonical curves? We like canonical curves. So what happens with canonical curves? So all this works for canonical curves, there's no problem. This vanishing hypothesis is not needed for all that to work over there, but it is needed for some of the other stuff. If C is a canonical curve, Clifford index greater than or equal to 3, which is the analog of the 2g plus 3 condition, at least sort of from the Green-Lazarus-Feld point of view. Secant variety is never arithmetically called Macaulay. Just isn't. Problem very simply is that this h1 of k not being 0 causes problems. It doesn't cause problems for the canonical curve because you're only interested in the h1 of the ideal sheaf, and so the h1 of that O of 1 doesn't bother you. When we're talking about the secant variety, worrying about arithmetically Cohen-Macaulay, we need h1, h2, and h3 of its ideal, and that non-vanishing causes problems. Causes enough that it's simply never arithmetically Cohen-Macaulay. At Clifford index 2, there is one that's arithmetically Cohen-Macaulay. There's, of course, a curve of genus 5 in P4, whose secant variety is a hypersurface. That's sort of cheating.
What about a prim canonical curve? That would be interesting for us.
Prim canonical curve.
Meaning, a canonical curve tensor a two-division point. So it goes into PG minus 1.
Yeah.
And has H1 equal to 0.
That
would
might
be
work.
interesting.
Yes.
That would be interesting.
The other problem that pops up is not for curves. Here's remark 1. Remark 2. In higher dimensions, things go bad. Sort of like canonical curves. So this doesn't make any sense, but I'll say if the dimension of our curve is greater than or equal to 2. If the dimension of your variety is at least 2, then the secant variety being arithmetically Cohen-Macaulay actually implies that HIXOX is 0 for I greater than or equal to 1. So it will not happen very often that these secant varieties are arithmetically Cohen-Macaulay. But it worked out very nicely for curves. Yeah. Okay. So this gives me enough confidence to formulate a general conjecture for curves. And this appeared, I think, in this paper here. We have a smooth curve embedded by a line bundle. of degree at least 2g plus 2k plus p plus 1. Then this k secant variety satisfies nk plus 2p. Where when p is 0 here, I'm looking for arithmetically Cohen-Macaulay. So nk plus 2p, that means that the ideal is generated by forms of degree k plus 2, and the syzygies are linear for p minus 1 steps. So k plus 2, 0 doesn't make any sense. We're going to call that arithmetically Cohen-Macaulay. So of course, this is true when k is 0. It's also true for all, okay, no, k equals 1. No, I wrote it wrong in my notes. It's true for all k and genus less than or equal to 1. Von Bothmer, Kulik in 04. Work this out for elliptic curves. And of course, the p equals 0 case now works for the first step anyway. So, how do you approach this? I don't see a way you approach anything like this anymore. So, we'll focus on the first secant variety. This is going to be n3p. So the first secant variety, this satisfies n3p if h1 sigma 1 wedge a m l b is 0. A is going to go from 2 to p plus 1, and b is at least 2. Notice the slight difference from what you usually would see for curves. We need b to be greater than or equal to 2 because we're looking for n3p, not n2p, so that shifts our degree by 1. Notice also that a is going to begin with 2 because the a equals 1 case is the arithmetically Cohen-Macaulay case, the projectively normal case. So here's our condition. If you remember the little calculation I did at the end of the talk yesterday, we saw that h1 sigma 1 tilde O2H minus E was 0. This actually implies that H1 O sigma 1 2 is 0 down below, which makes this equivalent. So we need precisely this vanishing. Now that's fine, but what's our problem? Well, first problem is that sigma 1's not smooth. We don't like things that aren't smooth so much. It would be nice if it were smooth. But we have a solution. We have a built-in solution. We're going to blow it up. We can blow it up and work on the smooth object upstairs. Generates, of course, a new problem. And the new problem is that Ri pi lower star O sigma 1 tilde doesn't vanish. Not usually. So our singularities are rarely rational. And once we don't have rational singularities, I hope I don't offend anybody by saying the word spectral sequence. We are stuck arguing with spectral sequences. I mean, in higher dimensions, right, none of these, in general, none of these direct images are vanishing. This causes all kinds of problems. But, oh well. I think I'm only going to mention spectral sequences once today, and it will be right now. How do we get at this? Well, and I'm going to use sort of the easiest piece of any spectral sequence you ever want to use. Just the 5-term sequence associated to Leray-Serre. I only need the first 3 terms, in fact. So how does the 5-term sequence go in shorthand? This is H1R0 to H1 to H0R1, the first 3 terms of the sequence. In our case, this would be H1 of this. To H1 upstairs. To H0 of the R1. Now it's unfortunate that we have an R1, but it's nice that it looks so pretty. Because this moves right down to the curve or to the underlying variety. This is H0x. And you think about what's going to happen here. Let me do it in 2 steps. So this is simply wedge A, M, L, B. Tension with that. Which is H0 X, wedge A, M, L, B. Tension with H1 X, OX. Now this is comforting because this is just working on our underlying variety. In some sense we should understand that. This isn't too bad either. We want this to be 0. There's only one way this is 0. We need this map to be injective. In general, it's difficult to show things are injective without showing that other things are 0. And so staring at this a minute, we hunt around for some sort of vanishing. And what we notice is this. What does this look like? This looks like something else. This looks like and this will either be illuminating or it won't be. It looks like this, where this piece has vanished. In other words, it looks like what we would have gotten had we gone to compute H1 X cross X, pi 1 upper star, wedge A, ML, B. just using the Coulomb formula. This is living on one factor. The other side is trivial. And if we assume that our underlying variety satisfies the correct NP condition, this is 0. This is the usual ML B. I lost my B. So if we assume the appropriate NP condition, this vanishes. That looks just like this. But we've seen this. This looks an awful lot like this. Notice the blowing up the diagonal doesn't affect anything here. So I may as well have written this as H1 that. Doesn't affect the cohomology. What this suggests is that this map from here to here is actually simply the restriction of this to the exceptional. And it takes a little bit of work, but it's not too bad, but you can show everything is compatible and everything works out correctly. So it turns out that this actually works, and that alpha will be injective if H1 sigma 1 tilde, stop writing these, B H minus E is 0. Crucially again, this won't vanish. So in some sense, we're saved by the fact that our singularities are not rational. This wasn't going to vanish anyway. This is what we're going to get to vanish. That'll give us our injectivity, which will give us our N3B. Okay, now, I'll also say, with this one's a lot more work actually, that also turns out to be equivalent. You can show the H0s behind its surject. The only way that that thing's going to be injective is if this vanishes. Sometimes comforting to know that you're doing the best you can. Okay. So how are we going to get this to vanish? Well, if we think about what we've got, sigma 1 tilde is a P1 bundle. For Hilbert 2, this is a P1 bundle. So we're tempted to take this and just push it down and work there. Two problems occur. One, the direct images here aren't so nice. The higher direct images vanishes, but the R0 is not so nice. And I don't know a lot about vanishing on Hilbert 2. So we're going to work a little bit harder here. In the end, this is still going to be our trick, but we need to clean this up a little. The way we're going to do that is we are going to look at the following sequences on sigma 1 tilde. I'm going to drop the pi upper stars because at some point we'll just remember them. So we have this sort of standard sequence coming from pulling the Euler sequence back up, and then doing other things to it. By the end, this is just the wedge ML to the wedge gamma to H, and then we tensor through by everything to to make this work. Now we want to understand each one of these. The idea is we're going to push them up. Our extra hypothesis is that this thing vanishes. We want hi sigma 1 tilde, sigma 1 tilde, BH minus E to be 0 for all I and B. Now that's fine. It's a bit of a cheat though, unless somehow you can understand when this is true. The reason this didn't bother me at first is because I know this is true for curves. In the paper Jessica Sidman and I wrote, we actually used this. So the curve case, this is just true at 2g plus 3. In general, the following condition will give this to you. And we find this, well, how would you get that to vanish? This is playing by pushing this down to the Hilbert scheme, looking at the canonical double cover of the Hilbert scheme, and sort of playing games. The nicest condition I know that guarantees this is that you want hi x cross x L to the R plus S L to the R I delta to the 2R to be 0, and I want I and R greater than or equal to 1, S greater than or equal to 0. And by the square tensor, I mean one gets pulled up on one side, one gets pulled up on the other side. So this is sort of a standard looking trick. I mean, you kind of know how to do these at least a little bit. Right, when R is 1, this is just some sort of conormal computation. I guess when R is 1, this is the wall map. For higher R, it's a little harder. But still, there are reasonably nice conditions you can write down that imply that are weaker than the NP conditions, frankly. So I don't mind putting that on there. I'll give you some examples in just a minute. So there's our new condition. What that does is that's killing the cohomology down the center and allowing us to take H1, wedge A of B, replace it with H2, wedge A plus 1 of B minus 1, and then replace that with H3 of A plus 2 of B minus 2, all the way up until we hit 2. I want to end up with 2H minus E. And it takes me several minutes every time I do this to figure out the right indexes, so I wrote it down. So now, alpha is injective if and only if H I sigma 1 tilde pi upper star wedge A minus 1 plus I ML 2H minus E equals 0. For I greater than or equal to 1, A between 2 and P plus 1. So we've always got these two things we need to deal with. We have an A and a B, and we have to do it for a bunch of A's and do it for all the B's. We've now traded this, we've sort of fixed our B and pushed it up to here. We're increasing our wedges now and growing our cohomology. But it's a reasonable trade. It's a reasonable trade for at least two reasons. Reason number one is 2H minus E. Again, if you remember yesterday's talk, 2H minus E is precisely the linear system that gave this morphism. 2H minus E lives on the Hilbert scheme. It's very ample on the Hilbert scheme. So now pushing this down doesn't cause much trouble. It lived there anyway. The second thing that is nice is I've traded my H1s for HIs, and I know a bunch of these vanish for free. And enough of them. One more step. And then I'll give you a nice little result. So now this comes from the Hilbert scheme. This doesn't yet. But watch. I'd still like to push that down. So I need to figure out what this looks like when I push it down. So I have, let me start here. This is on sigma 1 tilde. Push it down to the Hilbert scheme. If I push this down to the Hilbert scheme, pi lower star of L. L along a secant line. Remember, L is your embedding line bundle. L along a secant line is O of 1. So when I push this down, I'm going to get something of rank 2. And when I pull it back up, let me call this phi. Phi upper star of phi lower star of L is going to surject onto that. That's a nice rank 2 vector bundle. I'm going to call it kernel K for kernel, I guess. This, I'm going to call it E from now on. This has just as many sections as L, and in fact we get nothing going on there in the middle. On the left here we've got our ML. Kernel of this I will call ME, hopefully for obvious reasons. ME, you notice, has lower rank than ML. This injects into there, and my kernel is K again. Or my co-kernel is K again. What am I going to do with that? Well, now I'm going to look at this sequence. And I'm going to push this down. ME comes from the Hilbert scheme. So I just have to figure out what happens when I push down K. But look at this column here. L is O of 1 along the fibers. The fibers are P1s. L is O of 1. This is trivial because I pulled this back. K is O of minus 1 along my fibers. So all my direct images here die. So all the direct images of this go away. That tells me that when I push ML down, I just get ME. And so I can make this trade no fiber star anymore. Wedge A minus 1 plus I ME. And I'm going to replace that 2H minus E with 1, where 1 is my embedding line bundle down in the Hilbert scheme. Same condition. So we've done several things. One, by making this trade, we saved ourselves. We got one more free vanishing, because the Hilbert scheme has one less dimension. We have also reinterpreted our problem simply in terms of X. We're finally rid of the secant variety. Working on the secant variety was difficult. Now this is intrinsic to your variety. So we've moved the problem just onto the variety itself. It's always a good thing. Now, what do we get as a corollary of this? All those free vanishings mean that if you start out far enough, if you take your B large enough, it's going to run right away. This is giving us vanishings for a bunch of these B's. This is a regularity result. What we get is that your corollary looks a little different in dimension 1 and 2. I will stick with dimension 2. Let XD satisfy those hypotheses, satisfy sideboard hypotheses. And sigma 1 will be 2d plus 3 regular. I guess I don't need d greater than or equal to 2. When d is 1, we have a curve that's 5 regularity, which we knew. So at least in this sort of form, this is the best we're going to do in general. It's possible the correct answer is d plus 4. I don't know that, but 2d plus 3 works. And this is precisely, you're sort of going out 3 spots and down 2d of them to get your vanishings. There's nothing fancy there. This gives us a nice, simple regularity result on secant varieties to essentially anything. Now, I'll give you some examples because I still haven't told you when this is true. So for example, the first is actually improves the previous regularity result curve for curves. Here's a non-special smooth curve that satisfies N2 is now enough. We've given up that degree bound. Two, very general result. Smooth variety. Embedded by k plus m to the d plus 2, where m is very ample.
Which degree bound in one? Is it one?
K plus m ample. Excuse me?
In one. In this, which degree bound?
In this one?
Four.
No degree bound.
No degree bound.
Non-special and N2. So again, not canonical. I need this to be non-special and satisfy N2. So this is just a slight improvement of the 2g plus 3 bound, which I had before. This turns out to be a much better method than the method I used before. Three. Everyone's favorite. Just because they're clean, because canonical goes away. Out on an abelian variety. I guess it's really correlated with 2. Embedded by right way it's gone. M to the R with M ample, R greater than or equal to 5. I guess not a correlated of 2. This, though, again, in the case of elliptic curve, the correct degree bound is 2g plus 3, which is precisely n to the 5. So this is also as good as you're going to do. And one last one, Segre-Veronese embeddings of products of projective spaces. As long as all of your D's are at least 3. I need the D's to be at least 3 for this, for the 3 randomness hypothesis. If the D's are 2, you don't have the 3 random. There's lots of other ones. You can sort of play with this condition a lot. There's nice real theorems on when this vanishes for homogeneous varieties, and mostly coming out of the old work on the wall map and the higher wall and Gauss maps. When did I start?
20.
Ah, okay. I'll even have you out early, maybe. Okay. So this, again, we got for free, sort of for free. We had to work a little up front. And we're down to this condition. So the question is, when is this 0? Well, what we do now is we shift our focus a little. call this D, to this canonical double cover. And what we're going to do is we're going to find things on this that when we push them down, this bundle that I just erased will pop out as one of the factors. In practice, the things that happen, you take something up here, you push it down, it splits. One of the factors is the thing that you wanted. And so you can find your vanishing up here, very much like condition star over there. So the two things I have found that work. First, I don't want to say this as a corollary. I'll just say it this way. D lower star. So I'm going to work on this blow-up of wedge A minus 1 plus I ML two and sorry about that. L tensor L square L minus 2 delta. There it is. If you take D lower star of that, so this is living on one side, this is living on the other, and by minus 2 delta, I guess I mean minus 2 times E delta, the exceptional locus over the diagonal. If you push this down, you get wedge A minus 1 plus I M E 1 plus a mess. But we're not interested in the mess. What this tells us is that if we can get this to vanish, we can get this to vanish, which is no problem. This, however, sort of a standard trick, right? HI of this is again, this is a conormal bundle vanishing. So this is HI X wedge A minus 1 plus I M L tensor with the conormal 2. So if you can get this to vanish, you're all set. We can play with that a little bit. Corollaries. Suppose you have a smooth curve bent by line bundle of degree 3g plus 3 plus p, or 1/2 7g plus 4 plus p. It's only when p is large that it switches there. Then you would get N3P. In general, L sufficiently large works on any variety. Now, there is another vector bundle where D lower star pops out a factor. That one is wedge, I'm going to drop the indices for a minute, wedge A, ME, L, tensor L, minus delta. Just a single delta this time. This is also wedge A, ME, 1 plus some other stuff. So again, you want to get rid of this. But if you remember, we had this sequence a long time ago now, which I erased. It was 0 to ME, to ML, to this K. We saw that K was O minus 1 along the fibers of the P1 bundle. What does K look like when you restrict it to the blow of X cross X? It turns out to be O plus L minus delta. So what that says is that I can take exterior powers here, keeping track of that K, and I have an exact sequence that looks like wedge A plus 1, ME L plus O minus delta minus, yeah. Nah, no delta. Wedge A plus 1 to L, L plus O to wedge A, ME, L plus L minus delta. And it's that term on the right we want to get rid of. Now there's one thing we haven't done yet, and that is we have not used the projections. The first projection, this maps us back to the original X. This is just a part of that blow-up. The second projection is what's interesting. We haven't used this at all. Push this down the other way. What happens along your fibers? Think a minute here. So along the fibers, let's look at this sequence here, because this one's easy, there's no wedges. What does this look like if you restrict it to a fiber of pi 2? Again, this K is now L plus O plus L minus delta. So on the very right, you have L minus EP. So this is a fiber over P. In the middle, you just have an L, tensor L. I'm sorry, I lost an L. This is MLL. On the left, what have you got? This is precisely the same sequence we saw on Wednesday when we worked through Lazarsfeld's proof of Green's NP. Only we're only pulling out a single point. I don't know in the higher dimensional case if this thing splits into direct sum of line bundles. I don't need it. I only need it for 1 point. Works just fine for 1 point. This is ML minus EP L. So when you restrict this to a fiber of pi 2, you've got wedge A plus 1, ML minus EP, L. Notice what we've done here. We are trying to kill this with an A. By pushing this down, the H1 here, we've shifted this up by 1, and we've projected from a point. By the result of Choi, Kwok, and
Got it.
She's not here, that's good. That we saw Wednesday, we know that we reduced the NP by 1 by projecting. So here we reduced the NP, the level by 1 by projecting, but increased it by increasing that. So this is a change in 2. And now, I'll make a confession. I have temporarily bad news, because while I was preparing this talk, I realized, so, I had claimed that this was enough. Given this shift, I could show that if x satisfies np plus 2, that sigma 1 satisfies n 3p. And exactly here is where we see the shift by 2. When preparing this talk, I realized my argument has a gap. I've tried very hard over the last week to fix it. I have been unsuccessful, but it appears to be a gap, not an error. Does that make sense? There's something I can't verify to my satisfaction, but I think it's correct. But rather than pretend, which was tempting, to just pretend it still worked, I will admit that there's a little hole here. This still works fine. Hopefully, there will be another preprint in the next couple of weeks, or a replacement of the previous preprint in the next couple of weeks, where I will be able to patch this. I have some hope. I really have some hope. It's working. I think I'll be able to do this. But just to be honest, there's a little hole. But here you see precisely this shift. By pushing this down to pi 2, you get a nice short exact sequence. Your higher direct images all vanish. And so computing this, you can compute it down on the curve. And that is where or not on the curve, but on x, that is where I thought I had an argument that worked. It doesn't quite. But the rest of it still works. You push it down, it's still, the higher direct images still vanish. It's still a matter of killing the cohomology of that thing. So somehow, there's a way to do it. But I haven't yet. But I'm hopeful. Anyway.